The Einstein-Hilbert action or the Palatini action, which are equivalent, are okay for classical gravity, but they are not okay for quantum gravity. So we'll see that they have some problems when we will try to quantize them. And so we need to add more terms. And today we see which terms we will need. So this is the action here. It contains the cosmological term, the Hilbert term, and then you can add terms that are built with more powers of the Riemann tensor, quadratic, cubic, or built with covariant derivatives of the Riemann tensor. Some covariant derivatives of the Riemann tensor give nothing new thanks to the Bianchi identities, but some others do give something new. So, for example, you can build R squared, box R, R box R. Now, in principle, you can add infinitely many terms, but there is a unique, to some extent, theory which just contains the quadratic terms. So we just focus on the quadratic terms, because there will be enough for quantum gravity. Quadratic means they are built with two Riemann tensors. So you can have d4x e square root of minus g, and then you can build the following terms with arbitrary coefficients in front, which will be coupling constants if you want. R squared, you can square the curvature, the scalar curvature. You can square the Ricci tensor, or we can write it directly in the notation which is more familiar to us with space-time indices. So let's write square root of minus g. Here we write the Ricci tensor, and then we can square also the Riemann tensor. Actually, one can wonder whether these are all the ones we can write. Well, with the two Riemann tensors and without adding more derivatives will raise the dimensions. There will be what is known as power counting to tell us what are the dimensions of these objects. And basically, we have that the dimension of the Riemann tensor is equal to 2 because it contains two derivatives. Let's recall that the Riemann tensor is d gamma, and then there is a gamma gamma. And if you use, now we are assuming both vanishing torsion and the metric compatibility, then gamma mu nu rho is equal to 1/2 g rho sigma partial mu g nu sigma plus partial nu g mu sigma minus partial sigma g mu nu. And a metric necessarily has to have dimensionality equal to 0. That is because in the flat space you have eta, delta, mu nu if you want, or eta, mu nu in Lorentzian manifolds, which are numbers. And again, we give dimension 1 to an energy, so derivatives. So derivative has dimension 1, which means that gamma has dimension 1, and the curvature has dimension 2. So the terms we have built, we have introduced so far in the Hilbert action are what? This is a constant. Let's say this is 1, which has dimension 0. This is r, which has dimension 2. And then you can classify all corrections by means of their dimensionalities. So the quadratic terms are those that have dimension 4. And they are built with 2 Riemann tensors. And you cannot use, you can, if you want, add further terms which are cubic. So let's say r squared has dimension 4. Cubic terms could also be, actually these are quadratic, r box r for example, but r has dimension 2, box has dimension 2, r has dimension 2. So these are all objects that have in energy dimension 6. So these belong to a further class. So we stick to the quadratic terms for the moment. And are these the only ones we can build? Yes. So you cannot use derivatives. Why? There is actually another term you could write, which is covariant with dimension 4. That would be this one. But that is the integral of a total derivative, because that is the integral of an object like this. And you know that there is an identity that tells you, should be familiar with that from general relativity, that tells you that something like that can be written by exchanging del mu with square root of minus g, and del mu becomes just partial mu. So this becomes the integral of a total derivative. So we are neglecting, ignoring one term that is trivial. We will see that actually there is in between here another term that's also a total derivative. So instead of having 3 terms, we will just have 2. But that total derivative will be not completely negligible. It will be important sometimes, not for quantum gravity, not immediately, and not for the field equations. And then there is another term which, if you ask yourselves how many ways you have to contract two Riemann tensors. So you cannot use covariant derivatives. What else can you write? You could write, for example, del mu del two derivatives del nu del something r alpha, beta, gamma, delta, and so of dimension 4 with two derivatives and one tensor, you have this thing by invariance under general diffeomorphisms. You have to contract those indices with a metric. And so what can you do? Necessarily you have to contract two indices there, which means that you will get just the Ricci tensor. And then we have to contract those among themselves somehow. So if you contract mu with nu and alpha with beta, you get what we got before. The other thing you can do is to contract one of those and then the other. So the other possibility, the only other possibility you have is there is no need to exchange those two covariant derivatives because r mu nu is symmetric. R mu nu is the Ricci tensor. But you remember the Bianchi identity, a contracted Bianchi identity which says that del mu r mu nu is equal to 1/2 del nu r. And so when you use that contracted Bianchi identity that follows from metric compatibility and torsionlessness, which we assume here, then you will get just what we, apart from a factor 1/2, what we just wrote. So nothing new. So this is for the dimension 4 terms that can be built with two derivatives and one Riemann tensor. And then what about those that can be built with two derivatives, with no derivatives, and two Riemann tensors? They still have dimension 4. So let's say r mu nu rho sigma, r alpha beta gamma delta. How can we contract those indices? Well, if you contract two indices within the same Riemann tensor, you have only one possibility. You can contract those two and have a Ricci tensor. You cannot contract those two or the other two because they are anti-symmetric. So if one of those tensors becomes the Ricci tensor, necessarily, if one of the two becomes the Ricci tensor, necessarily you have to contract two indices of the other Riemann tensors among themselves, so necessarily you have two Ricci tensors. And then the only possibilities you have to contract the indices of two Ricci tensors are the ones we have already written, r squared, r mu nu, r mu nu. So it's sufficient now to consider two Riemann tensors where the indices are contracted not within the same Riemann tensor. All indices mu should be contracted with some index there, it doesn't matter which one. We can choose the first and the first. And then when the first two are contracted, for the second one, you have two choices. You can contract the second one with the second one, or the second one with one of the last two, because there is anti-symmetry in the last two, so you will have equivalent results if you contract the second one with gamma or delta. So from that we have two possibilities. Let's write them down. Square root of minus g r mu nu rho sigma r mu alpha beta mu nu alpha beta, or r mu nu rho sigma r mu alpha nu something beta. So now we don't have many possibilities, because here rho must be contracted with one of the other two. It doesn't matter which one, because they are antisymmetric. So alpha, we can say, becomes rho, and beta becomes sigma, rho and sigma. Again, and the same here down, because alpha has to be contracted either with rho or sigma, but we have antisymmetry in rho and sigma, so it doesn't matter which one we choose. So this is rho and sigma. So we have two ways to contract the indices of two Riemann tensors. Actually, the two are related by the first Bianchi identity. Which I recall is if you make the sum of the cyclic permutations of three indices, nu rho sigma, for example, nu rho sigma, plus r mu nu rho sigma, you get 0. So if you consider the second, r mu nu rho sigma, r mu rho nu sigma, we can write that as what? So we copy the first Riemann tensor, and instead of the second one, we make two. We write with a minus sign, so it will be the sum of the two cyclic permutations of those three. So we have rho nu sigma. We move one place to the right, rho nu sigma, plus two places, rho nu sigma. Okay. Now let's check what we obtain this way. So the first term is rho mu nu r mu nu sigma, and here we have what? R mu rho sigma rho nu. Now, we want to show that this is, apart from the minus sign, exactly like that. Why? Because you can exchange rho and sigma and move rho here, you will get a minus sign because the other one is anti-symmetric. And so that moves sigma by one place there. And then you exchange sigma with nu, because they are third and fourth in the Riemann tensor at that point, and you have another minus sign. So this gives the same. Instead, the other term there is, if you exchange rho and sigma, is that. So you lose the minus sign and you have plus r mu nu rho sigma r mu nu rho sigma. So that means that if you move this one to the left, you get 2, and then you divide by 2, you get that this contraction gives the same result as the other contraction. So this is nothing new, and actually there is a further simplification, because there is a relation between those three that's not evident, and that makes a certain combination of those three equal to a total derivative, which gives the Euler characteristic that we already met in a different context. So we study a particular combination of those three quadratic terms that is called Euler characteristics. Yes, okay. The Euler characteristic of a manifold is this object. It's an integral on the manifold and can be written as a form like that. So it's quadratic in R, and can be written like that. How to relate it to the three terms we have already seen. Let's use the usual tricks. There is the numerical coefficient in front is there for some reasons that we won't explain here. But anyway, RAB, that is a form, so let us write it like that. RCD is also a form. And then we will have epsilon ABCD. So we have 1 divided by 128 pi squared integral on M of what? 4 E's, EM, EN, EF, EG. You should remember that yesterday we saw what that gives. it gives the determinant E, here it is, times d for x times the epsilon tensor itself. So we have R A, B, M, N, R, C, D, F, G, epsilon, M, N, F, G, epsilon, A, B, C, D, the determinant E, and D for x. So again, these four give these things. Now we have two epsilon tensors, and we know that there is no contracted index there, so this is a little bit long to compute, but we have to do it. It's a determinant with four deltas. So delta, 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 delta. MNFG and NFG and NFG, and then A, B, C, D, A, B, C, D, A, B, C, D, A, B, C, D. Fortunately, the anti-symmetries in AB and MN, CD and FG will reduce the number of terms because many contributions are equal. So for example, the first two columns are obtained by exchanging M with N, so they will give the same contribution, the first and the second two as well. Yes. So let's compute it. One divided 128 pi squared, integral on M, E d for x, then we see what happens. So let's compute it here, for example. I think this is what I did here. The first is A equals M, and then we have this determinant. So A equal M means that this is the Ricci tensor Bn, because we contract the first and the third. So you have the Ricci tensor Bn. And then we have this determinant, and that will give essentially two terms. So we make introduce another parenthesis. So here you can have delta Bn times delta CFGD, and then the crossing will give twice the same result. CF will give a CF will give a Ricci tensor. GD, CFGD, you see, will give a Ricci scalar. So delta Bn times a Ricci scalar twice. And we have done that for this determinant. Then you have minus, you compute this one, for example, and then you will have this times this, and this times that, minus delta BF So we are computing this determinant here. We have done this. Okay. Minus, so we said delta BF, so minus delta BF. That means that out of these four indices, F will be equal to B. So RCD BG delta BF. So we are computing this contribution, then the crossing of those two. The other one is delta BG. Delta BF, delta BG will give the same thing. So we have already identified as a factor 2 here. So delta BF, delta NC, delta GD, minus delta ND, delta GC. But since there is anti-symmetry in C and D, this is another factor 2. So delta NC, delta GD. NC and GD. There. So this is the first contribution. And again, you have a Ricci tensor because we are contracting G, the second and the fourth index. Plus. So now we have to compute starting from here. But this will give, by anti-symmetry, the same contribution. There is an overall factor 2 front of everything, because as we said, this gives something which we have computed, this will give the same thing. This will give something which we will compute, and this will give the same thing. So what we just need now is to compute here from this one. Delta MC. So let's write what we get. R, we put M equal to C, AB, MD, R, M, MN, not MD, R, MDFC, G. So we have contracted these two. Now we want to see what we obtain. And, well, maybe we can just copy it and do it in the other slide, because it's a little bit long. Well, it's not long, but we cannot really see it nicely otherwise. So this is the minor. We have no minus sign so far because we're in the third place. Okay, so this is it. Okay. The first two terms there are 2r squared minus 4 Ricci squared. Let me write it like that. Switching to space-time indices. Plus what? Okay, we have R and delta and A. Here, which means that we contract the first with the fourth. That gives minus Ricci with the remaining indices, which are B and M. And then we have M and the rest. We have, so this one times delta FB delta GD minus delta GB delta FD. But by anti-symmetry in F and G, they give twice the same result. So it's sufficient to put F equal to B and G equal to D. F equal to B and G equal to D. And this is D. D. So that is it. Now we have here and here, delta NB and delta ND. Or, yes, we have to do them all that because there is no anti-symmetry now. So delta NB here gives plus the Ricci tensor with indices A and M, because we are contracting the second and fourth indices. But we have a minus because we are computing that in the second place. So that's again a minus. So delta NB times what? Delta FA delta GD minus delta GA delta FD. This gives a factor 2. So FA GD. FA GD. And that is again Ricci squared. The last contribution is delta ND. Delta ND, well, doesn't give anything, so there is a plus because we are not changing sign. AB MN delta ND MN, okay, delta ND, delta FA delta GB minus delta GA delta FB, again this will give a factor 2, and delta FA delta GB. F is A and G is B. And that is Riemann squared, you see. So now we just collect what we get. One divided by 64. Let me go back to the 32 we had because everything is multiplied by 2. 32 by squared. Let me also collect a minus sign in front so we get precisely the same coefficient we had. And then we have r squared. Okay, the minus will be done later. Let's not go too quickly. So r squared from the first minus 2 Ricci squared here you have a contraction between the second and the fourth, so this is Ricci squared with minus Ricci squared. Here also minus Ricci squared, so you have another minus 2 Ricci squared. Plus RABMN, RMNAB. So R mu nu rho sigma, R mu nu rho sigma. And yes, this is what you get. So this object here, which we still have to discuss, is the Euler characteristics, and it is a combination, a certain combination of those three terms. And now we will see that this combination does not contribute to the field equations because it is the integral of a total derivative. And it is the yes, it's better to write it down. So chi of m is minus 1 divided by 32 pi squared integral on m of RAB RCD epsilon ABCD. You can prove that this is the integral on m of the total of the exterior form of another form. So this is a 4 form, this will be a 3 form. And C is called Chern-Simons form. So RAB RCD epsilon ABCD is equal to DC. Does that mean that the 4 form on the right hand side is exact? No, that does not mean that the 4 form is exact. Why? Because we will see that to write the form C, we need, again, these indices. So it's locally exact. And that's enough to say that it does not contribute to the field equations. But like a volume form, it is not really exact on the manifold. And that means that this integral here will not be 0. It will be, however, what is called a topological invariant, and that is called Euler characteristics. And we have already seen that in 2 dimensions, the Euler characteristics is a counting of the number of holes of the Riemann surfaces, for example. So this is a kind of an interesting thing, because the difference between the total derivative we said before, we found before, this one is really a total derivative, because that thing can be written as the integral of a total derivative in a covariant way, let's say, independent on the coordinates, and here there are no Lorentz indices, no flat space indices, so that is truly an exact, the integral of an exact form. And where was it? Can write this as the integral of an exact form. Why? Because you have a, well, this is not written in as a form, but you can write it as a form. And basically that's the divergence of a current. If you want, this is a current. But that current is written in a covariant way. Square root of minus g, it's a density, vector density actually. And that is how it should be written to be trivial. Its contribution. So you have by Stokes' theorem that this gives a flux of that current at infinity. But here instead it will become clear once we write this C. We can write C only patch by patch, chart by chart. So it's not possible to drop that by means, this contribution by means of Stokes' theorem. So it doesn't make any sense to write that, because there is no form C globally. And again, this is due to the fact that even if this form is written in as a form, so it's very nice from the point of view of diffeomorphism, it's intrinsic, changes of coordinates are intrinsic, it's not written intrinsically in an invariant way as far as flat space indices are concerned. You need to use them, which means that that is also written locally. So it's a form from a point of view space-time indices, but it knows about the tangent space of your neighborhood where you, of your open set where you are working. And again, C, we can write this C already, yes, we can write the result. C will be equal to what? This epsilon ABCD omega AB T omega AB. So you need to write C, you need the spin connection. It's not enough. You cannot write it in terms of tensors or covariant derivatives. You need the connection. So it depends on the coordinate system you use. It's not invariant. So this is defined only chart by chart. And it is invariant under diffeomorphisms because it's a form, but it is not invariant under local Lorentz transformations because it uses the connection. And if you want, you can work out the transformation under local Lorentz transformation, the variation under local Lorentz transformations. which I recall imply that delta omega is equal to minus the covariant derivative of those parameters theta ab that we introduced for the local Lorentz transformation. So again, to summarize, we will show in the next hour that this thing can be written as a total derivative, correct, but not as a total derivative of something that we can write just by means of Riemann tensors and covariant derivatives or the metric, but something that needs the spin connection, or in with space-time indices, it can be translated into something containing the Christoffel symbols. Okay, let's stop 10 minutes.